Okay, let's move on now to different reactions that alkenes would undergo. So it starts from the very nature of alkenes. They are electron-rich. As you see, this pi bond is available, and this is electron-rich because of this pi bond. And this is what we are going to add, XY bond. This could be a diatom, or it would be a heteroatom, a hetero-di molecule. And the addition would occur at this pi bond, and the pi bond would be disappearing. That means anything which is electron-rich would give to some electrophile. This would have a nature of electrophile. So E plus, when we say E plus, is electrophile. So that means an electron-rich alkene acts as an electron donating, and something which accepts as electrons is called electrophile. So most of the reaction in alkenes is that the electron-rich double bond would be able to be transformed or be donated to an electrophile. So that is called addition reaction. So this is an addition reaction. The fact that the pi bond is less strong than the sigma bond, the pi bond can easily break and makes the addition reaction possible. So pi bonds are less stronger than the sigma bond. So one pi bond is not as strong as one sigma bond. So the pi bond is available to be reacting, that's easily can be broken and undergo addition reaction. So what you need to understand at this point is that alkenes would undergo addition reaction. So they can add XY molecule into the pi bond and form all sp³ hybridized carbon. That is sp³ hybridized carbon. So the addition always happens in stereochemically. There are two things you need to consider. The XY electrophile or the XY molecule could add from the same phase. That's called syn addition. Syn addition, when the XY comes from the same side. So both add from the same point. That means this is X, this is Y. So you have this, 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 this. So you have 1, 2, 3, 4, 1, 2, 3. X, Y would be adding from the same side. But if XY is adding when X adding from one side and Y adds from the other face, you would have a different outcome. So if this is X and this is Y, now you have this. So XY is adding from a different, so here Y is adding right here, and X is adding from that side. This is called anti-addition. So there is a syn and anti-addition. Okay? So we'll continue more on this. So now, let's go now very specifically to the addition of, for example, hydrochloric acid, hydrobromic acid. That would give you a different, this is called hydrohalogenation addition reaction, hydrohalogenation reaction. This is one of the addition reaction. So when we say hydrohalogenation, we are adding HCl, HBr, HI, and so on. So in place of XY, now you could see these groups, HCl, HBr, HI. So the addition of this hydrohalogenation would happen in a way that to form alkyl halide. So the result of addition of this, for example, if you have this alkene and you are adding HX, one of the chloride, bromide, or iodide, the product would be one hydrogen here, one chlorine, one X here. So that is hydrohalogenation. So that is a pi bond is broken. This pi bond is broken, and the sigma bond is still there. So you are adding a new sigma bonds are formed. One sigma bond is formed here. One sigma bond is formed here. So by breaking the pi bond is broken. And you are making two sigma bonds that are formed. Two sigma bonds are formed. So that is the hydrohalogenation, to add this. So on this fact, I will be just forming first a tabular presentation of what an addition reaction looks like. For example, with a real molecule, you can add HCl and you would form, if this was H, you have Cl here, H. So you are forming an alkyl halide with this scheme. So this is called hydrohalogenation. But what we add to the double bond is also varied, because you can have several different reagents. Obviously, these are the most common one you can add, but I will show you different reactions first before we proceed into details of the reactions. Okay, here by using cyclohexene as an example, I'm going to demonstrate the different reagents which are common to any alkenes that happen as addition reaction. For example, in the top one, it's called hydrohalogenation. That means, I will just put it like this. So in this case, you have this, that. So the first one is hydrohalogenation. Hydrohalogenation reaction. So when you have HX, that means hydrochloric acid, hydrobromic acid, hydroiodic acid, you would be adding across the double bond. That is hydrohalogenation. And the product would be, you would have H and X added. That is hydrohalogenation. So X can be chlorine, X can be bromine, X can be iodine. The second reaction across the double bond is called hydration. This is a hydration reaction. I will just write it here. A hydration reaction. That means you are adding 1 mole of water to the double bond. So in acidic condition, you could reverse this. If you remember, we have dehydration using acid. This is hydration. So you are adding back the water. So it's a reverse reaction. We'll discuss on mechanisms. So it would add H and another OH. Basically, you are adding water. So it's called hydration. So remember now, these are different reactions of an alkene, any alkene. It could be an open chain, but we are just taking an example of cyclohexene. Here, this is halogenation. That means you are adding both across the pi bond, you are adding halogens. So this halogenation results in the addition of 1 molecule of a halogen. That is, it could be XX. So it's dibromo dichloro based on what you have. So, for example, Cl2 would add 2 chlorines. Example would be you can have a dichloride compound. That's halogenation. So you should use molecular halogen. That means chlorine gas, bromine also as a reagent. This is called Halohydrin formation. Halohydrin formation is the addition of one OH group and one halogen. So this is called halohydrin. Halohydrin. In place of water, where it has H and one OH, here there is one OH and one of the atoms of the halide. So it could be X and OH, halohydrin. That's, for example, if you are using chlorine in water, you'd add a chloride and an OH. So look at now the different reagents that an alkene can produce. This is called borane. This is called borane because it adds one molecule of water, but the reagent is called borane. We have a reason why we are using borane. The reaction is called hydroboration. Hydroboration-Oxidation. I will not just leave it like that. It's called Hydroboration-Oxidation. A Hydroboration-Oxidation reaction is a reaction where in a controlled way you are adding 1 mole of water across the double bond. Why you don't do this? There are cases where your substrate might be very sensitive for a very strong acid. You would use a very mild condition because in the synthesis there are different things you have to consider. But it does the same thing like this one, but in a very controlled way. So it adds water molecule. Basically it's on OH and H. 1 water molecule is added. The last one, which is very important as well, is hydrogenation. Hydrogenation reaction is a reaction where you saturate the double bond with hydrogen. So it becomes cyclohexane completely. So hydrogenation reaction. It needs always a catalyst. It's a palladium or platinum catalyst is used in hydrogenation reaction, and the product is a complete saturation by hydrogen. 1 mole from 1 mole of hydrogen gas, you'd add both 1 mole of hydrogen is added and it gets saturated. So from cyclohexene, you went to cyclohexane. These are just a summary of like an index card of reactions, which you need sometimes to memorize, but the mechanism is much more important. I haven't discussed yet how they add. There is a clear mechanism for all of them, and I will discuss each in the next section. But initially what you need to know is an alkene with a pi bond is very susceptible for addition reaction because it's electron-rich. The electron-rich alkene would look for an electrophile first. It would pick up that electrophile and then subsequent reaction continues. So some of the reactions an alkene undergoes would be hydrogenation, hydrohalogenation, where you add a halogen and hydrogen, hydration, where you add a hydrogen and OH group, which is addition of water, halogenation, you are adding a molecule of chloride or bromide. That means you are adding a dichloro or a dibromo. Halohydrin is addition of 1 halide and 1 OH group. It's like addition of water, but instead of H, you have the halide. So you react. These are the reagents also you need to remember. Hydroboration-Oxidation. Whenever you see borane, it is just the addition of water in a controlled way. So this mechanism I will explain later. Hydrogenation is a unsaturated acid, unsaturated alkenes are converted into saturated alkanes by hydrogenation. That means This is a unsaturated, 1 degree of unsaturation. You want to convert it to saturated system, you use hydrogen over a catalyst, which can be a palladium or a platinum catalyst. With this, I will continue now more in the discussion of the mechanism of the addition reaction over the alkene bond or the pi bond. Now overall, we have been just discussing what the addition reaction was for alkenes. Alkenes, they undergo addition reaction, and of various reagents, we have just listed how they will be added to make the saturated bond after the addition reaction. But here I want to give you a mechanism of hydrohalogenation, which is addition of a hydrogen and a bromide, or hydrogen and a chloride, HX. So basically we can just put this addition of hydrohalogenation, which is HX. The mechanism is important for you to understand what happens in the overall reaction. So I will start by pushing arrows and show you exactly what happens in the mechanism. So the initial reaction mechanism would be at a slow step where the loose base, this is a loose base, that means alkene is considered or act as an electron-rich center where it is as a base. So it would act by just pulling off a proton first, which is a slow step, and forms this intermediate. This is a newly added hydrogen, and a carbocation is formed. So remember, this hydrohalogenation is a two-step mechanism. Now, after the carbocation is formed in a fast step, the Br minus with its full negative charge would come and attack that carbocation. This is a fast step. So overall now what we will form is the addition product, which is CH3, HBr, HCH3. So this is the addition product, and that is the mechanism. Initial abstraction of a proton by a loose base, which is the alkene double bond, would grab that proton and form a carbocation, a stable carbocation. Then the Br minus, which can act as a nucleophile, would attack that center. And finally, you would have that product. So what we learn from here is now there is a formation of two strong sigma bonds are formed, and it is an exothermic reaction. So first, let's summarize this. This is a two-step mechanism, hydrohalogenation. And the rate law follows second order reaction. What it means is at the transition state, at the highest energy transition state, both the alkene and also the hydrohalide are implicated. So rate equals K times the alkene concentration times HBr or HX in general. So I'll just put it like that. That's HBr. So this is what we see in the mechanism of hydrohalogenation. How about the energy diagram? The energy diagram also reflects the second order kinetics for hydrohalogenation through a carbocation intermediate. Now, the initial starting materials are down here in the energy profile. The intermediate that initially comes, the HBr, comes across the double bond. So this starts to weaken up. So this is a weakening. The H is being added. The HBr bond is being broken, and Br is starting to come in. So that is in the transition state where the highest energy is, that's where it's required, and it is the slowest step. So that's the transition state. So in the intermediate, the carbocation intermediate, which I showed here, is this one. And the carbocation is relatively stable. Now the Br minus starts to make a bonding between this carbon and this sigma plus center. And finally, the Br would attack and forms this product. So as you see, delta H is less than 0 because very strong 2 sigma bonds are formed, the Br and H, and a very weak pi bond is broken. And obviously the HBr is also broken to give that final product. So this is generally the hydrohalogenation mechanism. It is what you should remember is it is a two-step mechanism. It goes through carbocation, and the nucleophile comes and adds or attacks that carbon center. But in the next section, we'll see where should, if you have unsymmetrical alkenes, meaning that if you have CH3 and this was a hydrogen, where does the carbocation actually forms? Because there are two chances. It can go like this or that way, and the carbocation could be on this carbon or on the other carbon. So that we'll be discussing in the next section. It deals with, there is a rule called Markovnikov Rule that would tell us that the carbocation should form on a more substituted side of the carbon or the compound. So that's Markovnikov's rule. We'll discuss that in detail more in the next section. Here I want to show you an additional reaction, which is a hydrogen chloride in both cases. And at this point, I want also introduce the Markovnikov rule, which is very important in the addition regioselectivity, or you can call it chemoselectivity. So what we see here is in the mechanism, if you remember, we were able just to pick up that proton, and the carbocation would be here or there. So in the first case, for example, if I have H here, H here, H is added here, that means if the carbocation is formed here, this is one possibility, Cl minus is around. And in the other mechanism, if you just do this, CH3, and pick up that, a plus, a hydrogen, and 2 hydrogen, and the third hydrogen, which is the new one, which was. So these are two possibilities in the addition. Either the chloride would come here, or the chloride would come over there. So what that result would be is a different product where chloride would come here, or chloride would come here. But according to Markovnikov rules, always the carbocation should reside on a more substituted carbon. More substituted carbon will have the carbocation because that is the most stable one. This is what Markovnikov rule tells us. So according to Markovnikov, this has a metal group. This is hydrogen. This is hydrogen. So this is the more substituted carbon than that carbon. This is a more substituted carbon than that. So this, in this case, according to Markovnikov rule, this product would not form. Rather, what we form is this product where the chloride goes to the more substituted carbon. So this is how the addition should go. So according to Markovnikov's rule, the addition of any HX hydrogen halides, HX, I would say in general, HX addition. According to that, the electronegative atom would go to the more substituted carbon, because that more substituted carbocation is much more stable than the other one. So if you just look at this, the addition in terms of energy diagram, if I say this is case A and this is case B, the activation energy for case A is much, much higher. And for B, it is like this. So B goes before A happens. So B is the one where Markovnikov will allow us, based on the stability of the carbocation. So this is one thing we should know. Markovnikov rule states that the substitution or the addition of a hydrogen chloride or any HX preferably goes for the halide on the more substituted carbon, because that more substituted carbon generates a more stable. For example, this is a secondary carbocation, because there are two carbons. So this is secondary. This is only this one, so it's a primary carbocation. So A is a primary carbocation, but B goes through a secondary carbocation. And one thing you don't forget should be in the addition, if there is a possibility of even going to a tertiary by rearrangement, that is also a possibility. So I will do one example where we have a carbocation rearrangement that happens during the addition. So next I will show you an example where a carbocation would rearrange and form a more stable one, and the addition occurs under in that manner. So we'll see that next. Okay, here I have this alkene, and we are going to add HBr across the double bond. So this is an addition reaction, which we have learned. An alkene would add HBr, and the addition would be along this double bond, carbon-carbon double bond. So let's do initially, okay, if I just grab this, obviously the carbocation should not be on this, but on this one, according to what we have discussed by Markovnikov Rule, the H should go to the less substituted carbon. Okay, let's just start writing that out and see what we get. So you have this, CH and carbocation, and CH3 is formed because this hydrogen is added on this one. So one hydrogen is added on that one, carbocation stays there. So according to Markovnikov, that's what you just generate first. But there is even more things you have to consider in this case, where the carbocation can be even rearranged. So don't forget, remember carbocation rearrangement in this case. Rearrangement. So because this is secondary, now if I do carbon-cation rearrangement where there is a metal shift from here to there, so this is 1, 2, 1, 2 metal shift, I can generate a tertiary carbocation. So that's preferable. CH3, carbocation is right here. Remember, Br is still floating around. So this would have CH3. This is a migrated methyl to that, CH3. Now I have a tertiary carbocation. Now the bromine attacks on this carbon. So the addition, apparently this was a carbon 1, 2, 3. You would expect H and Br here, according to the addition reaction over alkenes, but there is one more factor as well once the carbocation is formed, which is rearrangement. Don't forget the rearrangement. Tertiary is much better. So the final product would be CH3, C, CH3, Br, CH, CH3, CH3. So this is the final product. Now, if you look at it, the addition happened over this carbon and that carbon because it went through a carbocation rearrangement. So usually you have to be careful and considering both Markovnikov Rule, Markovnikov type addition first, and then carbocation rearrangement, if possible, if there is one that can happen. These are the two factors you need to remember when you are adding across a double bond. Okay? We'll see now next how about the stereochemistry of addition of HBr or HX overall, what it looks like in terms of stereochemistry. That we'll see in the next section. Okay, now continuing our discussion on the addition of HCl across a double bond. It is also stereochemically important to understand the addition could happen as a syn or anti-addition. I have previously mentioned that the addition of HCl or HX in general could be a syn. Syn means that they will come both HCl, both H and Cl can come from the same face or from the same side. So what it means is this is, as you see, this is sp²-hybridized carbon-carbon bond. So basically this group is flat on the board, or it is like something like this. So both H and Cl can come from the same face. So they can come either from here or here, but in any case they would come from the same face. But it could also happen that since this bond is broken, H can come from top and Cl can come from bottom. That is called anti-addition. So let's work on this. So if you just have a syn addition to this, a syn addition would give you, obviously the carbocation would be here, so the Cl would be on this side and H would add on this carbon. So let's consider syn addition. The syn addition results, meaning from top, both would be coming. So this is H, this H, and this H is this one right here, but the other one would be just this hydrogen. This is what is being added, and if you have this carbon right here, Cl would come here from bottom, and this is actually anti-addition. I'm just showing anti-addition. So this would be the propyl group, CH2, CH2, CH3, and this H is this, the one, not CH. CH2, CH3 is this group right here. So these are the two groups that are added. So this is an anti-addition. Okay, this is anti-addition, and for the syn addition, so this is anti. Let's work on a syn addition of HCl on the same. So when we say syn, it should be like the hydrogens. This hydrogen is down here, and H is coming from top, let's say, and Cl is also coming from top, the same side, syn. So this is the propyl group, CH2, CH2, CH3, and this is the ethyl group, CH2, CH3. And here I have this H, and this H would be here. So what it shows us is this HCl is added from the same side. So this is anti, H and Cl are added this side from opposite. This is added from the same. So this bond is made like this, HCl. So this is a bond that's newly made, Cl. So there is syn and anti. So the syn and anti also can come from, also for anti, for example, you could have Cl here and H would be here. Or Cl would be here, H. There are 4 stereoisomers that could be formed, because this syn addition is coming from top, syn addition can come from bottom, and also syn addition can have from. So 4 stereoisomers are possible, 1, 2, 3, 4. But whether they are different or the same, we'll have to check out assigning the stereochemistry. For example, this is the syn addition. Let me draw another syn addition for this, another enantiomer. For example, if they come from bottom, they will look like this is H, this is another H, and the new H is coming from bottom, and the Cl is coming from bottom, the same side. So this would be CH2, CH2, CH3, and the ethyl group is this, and Cl is down here. So HCl is coming from bottom, HCl is coming from, so those are enantiomers. So if you just look at this and assign stereochemistry for this, what do we get? So this is priority number 1, and priority number 2 would be, this is 3 hydrogens, the carbon, but this one is, this is number 1, this is number 2, this is number 3, this is number 4. So if we go this way, this would be an R, but since the lowest group is not at the behind, this is an S. Let's see here. This is group 1, and number 2 is this carbon right here. Number 3 is this one, Number 4 is this one. So this is 1 to 2, that is an S, but since it is not at the back, the lowest group, that's an R. So those are mirror images, enantiomers. Enantiomers. And this one also would have another enantiomer, plus the enantiomer. So syn addition from bottom or top, but in the same side, anti-addition in opposite side. So this can add chloride from here, and H can add like that. So anti would have 2 pair of compounds, those are enantiomers, and syn could have 2 mirror images, enantiomers. Remember, in the stereochemistry of syn addition and anti-addition. And remember that the Cl goes always to a more substituted carbon. That's the Markovnikov Rule. And don't forget as well, if there is a possibility for carbocation rearrangement, that's also one thing you need to remember. So this is how we add syn or anti. For syn, there are 2 possibilities. For anti, 2 possibilities, generating enantiomer pairs. So 4 different compounds can be just made by a single addition of HCl. So all these 4 compounds are possible from just one reaction. So it's not like two reactions separately. This is just to show you that HCl can add in anti or syn, but the anti and syn also can be producing stereochemically pure enantiomers. So these are enantiomer pairs, these are enantiomers. So this gives you 4 compounds. The relationship is stereoisomeric compounds. These are stereoisomeric, stereoisomers. Okay, so we'll continue more on the stereochemistry with some more examples. So from just what we have discussed, we have produced 4 different compounds. It looks like 4 different possibilities, not compounds. Now from syn addition, you get mirror images. These are syn addition, one from top and the other from bottom. They are related as enantiomers, meaning A and B are enantiomers. And if you just do anti-addition, meaning that hydrogen from top and Cl from bottom, and if you just do hydrogen from bottom and Cl from top, you get enantiomer pairs. But what you should be careful here is that you have to understand what that stereochemistry right there, and right there. So from what we see here, out of 4 possibilities, B and C are actually same compounds. B and C, if you just look at them, they are same compounds. And A and D are same. A and D, if you look at them, they are the same compound. So in actual case, even though there are 4 possibilities for this particular compound, because we don't have a stereocenter here, only 2 compounds are formed. Those are 2 enantiomeric compounds. They are mirror images to one another. That's why they are 2 different compounds. For example, from B, if you take B and A, B and A are mirror images. Or if you just take C, for example, C and A, for example, C and A are also mirror images. Therefore, the net number of compounds are 2 enantiomeric compounds. So usually when in an exam or in exercises, you make sure that you display everything. Once you are done with showing all of the possibilities, then check what that relationships are. They could be the same, they could be enantiomeric compounds, they could be diastereomeric compounds. But here, this is simplified because at least this carbon is not a stereocenter because it has 3 is the same things on it. So that cannot be a chiral center. So this is simplified because that carbon is not a chiral center. So we have only one chiral center, which is this is the chiral center. 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 So, but this is not always true that this could also be a chiral center. Then you get a lot of different number of compounds. So that will be very complicated. But make sure that you lay out everything, the 4 different possibilities of syn and anti-addition. Syn can be added from top, syn added from bottom because they give you the enantiomers. And anti also can be one hydrogen could be from bottom, top, Cl could come from bottom. Here hydrogen is coming from bottom, Cl is coming from top. So make sure that the stereochemistry is well identified. So I will also encourage you to identify whether this is R, this is S, R, S, and so on. So make sure that what this is, whether it's S or R, R or S, S or R, R or S, so on. So that's how you would identify actually whether they are the same compounds or they are enantiomeric compounds. Okay, so we'll continue more on this.